Hello and welcome to this next lecture on data structures and algorithms. Starting today, we will discuss an interesting problem called string matching, and the problem of string matching is about finding a textual pattern, let us say call it P, in a set of strings S1, S2 and so on. You come across this very often in textual editors such as Vim or gedit, or you have this Unix command grep. This pattern P could be any regular expression. So we will discuss both extremely naive algorithms as well as efficient algorithms for such pattern matching. So formally the problem is to find all the valid shifts with which a given pattern P occurs in a given text T. More generally, the text T could be a set of strings, as we pointed out in the previous slide. And here is an example. You are provided the string S and below is the pattern P. So you want to find instances of STY in the string S. You start from the leftmost end, S equal to 0. You find that there is a mismatch at the third position, though there is a match in the first two positions. You can then think of moving the pattern to the right, scanning at the second character position of the string. You find a mismatch right away. Further down, you again find a mismatch at E and then at P. However, at position 5, which corresponds to index 4 of the string, you find a match at all the three positions S, T and Y. So this basically results in one pattern match. You can continue this process if you are interested in finding all the pattern matches. You might stop here if you are interested only in finding a single pattern match. So assuming that you are interested in all pattern matching, you look at index 5, find a mismatch right away, index 6 there is a mismatch. Now do you need to proceed? Well, it does not make sense, because you certainly cannot let the index overflow n minus m, or the index position corresponding to the number of positions in the string minus the number of positions in the pattern. So this is the naive string matching algorithm that we just illustrated. Given a text T of size n, pattern P of size m, you keep track of the shift index S at every point of time. So the shift index S is what you preserve into the text T. The pattern P at this instance of time will be scanned starting from this position S. So for S ranging from 0 to n minus n, and we are interested in matching the entire pattern, so S will be restricted to the number of positions in the text T minus the number of positions in the pattern P. So for this range of S, you are going to keep track of the position J. The position J is basically the index into P. So you vary J over the positions in P and do it till J is less than m. So J starts with 0 and maximum value of m minus 1. You are going to match Ts plus J with Pj at every point of time, and in case there is a mismatch, you terminate. So continue scanning P as long as there is no mismatch with T. So once you are at the end of P, you flag a match, print valid at shift S. That's what it means to have a match. And we are interested in all matches, and because of that we continue the scan. If we were not interested in all the matches, we could break right after printing the valid statement. Analysis of this naive algorithm. The inner loop is going to be called at max m times, order m times. This is assuming that you have a match at every position. So the worst case situation is as follows: T is A, and P is say A, M is 2, N is 6. So you're going to scan all the positions of P for every position in T, because match occurs at all or n minus m plus 1 positions. So this will result in C1 times m in the worst case for each position S, and overall you will have to do this for every position in T, which is n minus m plus m. So overall there are n minus m plus 1 into C2 calls overall, and this results in n minus m plus 1 times m overall complexity. What we'll see in some of the subsequent discussions are more intelligent algorithms which avoid this brute force computation by explicitly caching or memoizing some of the computations that were already done and reusing them. Some of the algorithms, such as dynamic programming, are in some sense brute force because they do consider all possible configurations, but they leverage previous computations in order to avoid redundant or repetitive computations. We will see some of that flavor in the algorithms that follow. Thank you.